Welcome to this explainer. Today, we are diving deep into analyzing troubleshooting that occurs during the injection molding process, and more importantly, knowing exactly how to fix it. We're going to transform what is often a super frustrating trial and error exercise into a highly systematic science. If you've ever stared at a rejected batch of plastic parts and wondered where on earth things went wrong, well, you are definitely in the right place. Okay, let's dive right into this. So we've got to start with this pretty fundamental question. Why do perfect plastic designs actually fail in production? I mean, you can have a flawless 3D model, totally impeccable math, and a brilliant concept, but the second that molten plastic hits the steel, reality takes over, right? But here's the good news. Manufacturing defects are essentially solvable puzzles. They leave clues, and today, we're going to learn exactly how to read those clues. Here is our roadmap for today. First up, the troubleshooting hierarchy. Then, flow and fill failures, followed by the critical cooling phase. After that, we'll hit material and operator variables. And finally, mastering the fix.
Let's jump into Section 1, the troubleshooting hierarchy. Because before we even try to fix a defect, we must first know statistically where to look for the root cause.
Okay, check this out. This data comes from a massive 30-year study by Texas Plastic Technologies that analyzed process-related defects. Now, in the industry, there's this long-held belief that the plastic material or the machine operator is usually the one to blame. But look at these numbers. A staggering 60% of the time, the molding machine itself is the culprit. That's followed by the mold at 20%, the material at 10%, and the operator at just 10%. So the big takeaway here? When you're troubleshooting, the absolute first place you should look for a solution is the machine. 6 times out of 10, your answer is waiting right there. Moving right along to Section 2, flow and fill failures. This is the physical stage of the process where the molten plastic is actively traveling from the hopper through the heating cylinder and flowing straight into the mold cavity. Now, you might have run into this before. A classic short shot or a non-fill. It's exactly what it sounds like. It's an incomplete molded part caused by simply not having enough material injected into the mold. When we visualize the flow path, we know this happens because the plastic cools and solidifies way before it can fully pack the cavity. This non-fill condition can actually be an extension of a flow line or a knit line issue, where the material literally just runs out of momentum and heat. So, what causes this? Well, a major machine variable here is injection speed. It determines how fast that molten material gets pushed into the mold. And man, is it a delicate balancing act. If your injection speed is too fast, the material tends to tumble and get all turbulent. This traps air and gases right in the resin, which then show up as annoying bubbles because the gas can escape through the vented areas. On the flip side, if your speed is too slow, the material cools off and solidifies too early, and boom, you get those short shots we just talked about. And this brilliantly illustrates a really severe consequence of going too slow, delamination, or what some folks call fish scaling. As the material enters the cavity in layers, a slow fill speed allows those layers to solidify before they can properly pack and fuse together. This weak bonding means the layers physically pull apart as the part cools and shrinks. It's a total structural failure. So what's our detective's cure for this? Actually, it's pretty straightforward. For both delamination and short shots caused by slow speeds, your immediate solution is to speed up that injection fill rate. You'll also want to optimize the cycle time to fit the specific material and the wall thickness of your part. Just remember, if bubbles start showing up, you've gone too fast and need to dial it back a bit. It is all about finding that Goldilocks optimal flow window. Let's move into Section 3, the critical cooling phase. Once that mold is filled, the part has to cool down. And let me tell you, this is where a massive portion of aesthetic and structural defects are born. Since injection molding is incredibly susceptible to temperature variations, uneven cooling rates across a part will just wreak havoc. You get warpage, which is basically differential shrinkage, making the part bend out of shape. You get sink marks, those little depressions on the surface that usually pop up in thicker sections where the plastic cools a lot slower. You've also got internal stress and cracking when rapid cooling pushes the material way past its limits. And finally, dimensional shrinkage, leaving you with parts that just don't measure up to the specs. When we compare these simulations of weld line and air trap analysis with volumetric shrinkage, you really see the physics at play. As the temperature drops to the mold's opening temperature, the product naturally wants to shrink. But these thermal dynamics are heavily dictated by the part's geometry. So wherever plastic flows have to split around obstacles, or wherever thick walls hold on to heat, the physics of cooling practically guarantee exactly where your defects are going to physically appear. Which brings us to the physical result right here.
Knit lines, also known as weld lines. See that little V-shaped mark? That happens when two or more flow fronts meet up but totally fail to knit together. When plastic flows around a hole or some obstruction, it disperses. If it loses too much heat during that split, the flows mix, but they don't chemically connect. This doesn't just look ugly, it literally creates a structurally weak area in the molded part that can easily snap under stress. To restore both the strength and the looks of the part, we have a rapid-fire checklist of fixes. First, you can increase the melt and molds temperatures so the material stays fluid just a bit longer. You can also crank up the injection rate or pressure to force those weld line areas together. Now, if it's a mold design issue, you might actually need to physically expand the runner channels and gate size, or even completely reposition the gates so the flow is easier and less obstructed. All right, let's shift gears to Section 4, Material and Operator Variables. We are finally tackling that last 20% of our troubleshooting hierarchy.
Brittleness is a prime example of a machine and a material issue teaming up against you. This is when a part cracks or shatters under conditions it absolutely should survive. A major, often hidden cause for this is an improper injection screw design. If your screw has a compression ratio that's too low for the specific resin you're running, it just won't properly mix and melt the material, and that leads directly to weak bonding of the individual plastic molecules. So the diagnosis for brittleness usually comes down to one of two things. If it's simply a pressure issue causing poor filling and weak weld lines, you just increase the injection pressure. Easy. But if it's that molecular bonding issue we just looked at, the fix is structural. You actually need to call up your material supplier, find out the correct compression ratio, and swap out that general-purpose screw for one that's custom designed for your resin. Another really tricky aesthetic defect is low gloss, which you'll see as a dulling of the product's finish. Now, while this looks for all the world like a material problem, it's actually most often caused by inadequate injection pressure. There simply isn't enough force pushing the molten plastic hard enough against the polished steel of the mold cavity to replicate that nice high-gloss finish. And hey, we can't forget the human element here. Operators account for about 10% of defects, and the absolute most common human error is inconsistent process cycles. When someone runs a machine manually and delays opening or closing the mold, it causes erratic heating of the material just sitting there in the injection barrel. If colder particles get into the mold, they break up the flow fronts, which stops the part from filling properly or creates nasty weak spots. Which leads us to our fifth and final section, mastering the fix. We've looked at all the variables. Now let's pull it all together into one unified troubleshooting mindset. These best practices right here are your systemic fixes, the ones that eliminate multiple defects all at once. To kill operator inconsistency, run your machines on automatic cycles. Use a robot if you have to, and only rely on manual operation for emergencies. Make sure your materials are dried perfectly. Constantly check your mold water lines for leaks or blockages, and always verify that your machine's screw design actually matches what your material supplier recommends. I want to leave you with this awesome thought straight from our source material. Understanding this concept will make the troubleshooting process less of a mystery and more of a science. The next time you face a delaminated part, a short shot, or a frustrating weld line, remember the hierarchy. Check the machine first, visualize the plastic's journey, and apply the exact scientific fix required. So the next time you're staring down a tray of rejected, defective parts, are you going to rely on blind trial and error, or are you going to use the data to crack the case? Thanks so much for joining me on this explainer.